Today we're learning about 6.3 in Stewart volumes cylindrical shell method. We're using Calculus Early Transcendentals by James Stewart. What is the objective for today's lesson? The objective is to compute volumes using cylindrical shell method and or washer disk method wherever appropriate. So here we have an example where we want to see this y equals 2x squared minus x cubed, the volume that is generated by rotating this area here underneath this curve between 0 and 2 around the y-axis. Now, traditionally, we could try to use the washer method, but with the washer method, that would need us to write x is equal to some kind of function of y. But because this equation cannot be solved explicitly for x, this is an implicit equation. So we would need to find another method, and this method is called the cylindrical shell method. Basically, we're going to choose a representative rectangle and rotate that rectangle around the y-axis to generate what's called a cylindrical shell. Then we'll do this for every rectangle within this this domain, 0 to 2, and let n tend towards infinity so we get infinitely many rectangles, and thus would create an exact volumetric solid of revolution. So let's talk about only the case where we're rotating about the y-axis for purposes of this video. So let's take a look at cylindrical shell in action, and I will exit my marker here. Does it pop up? And we want to see our cylindrical shell in action. So here we go. Here's our cylindrical shell. We do see that when I have a representative rectangle and I rotate that around the y-axis, that creates what's called a cylindrical shell. And we see that there's some thickness, some height, okay? And that thickness can vary depending upon how thick our representative rectangle is. It could be very thin, it could be very thick. So we have an inner and outer radius for a cylindrical shell. Usually inner radius we call R1. R2 is the outer radius. And we see we can have this happen. And we want to get a good approximation, we want n cylindrical shells, but we'll let n tend towards infinity, thus giving us a V is equal to a volume, an exact volume for this solid of revolution. Okay, so that's where we're going today. This is a fun thing to play around with. I do suggest everybody play around with this. It's on the slide. You can download the slide and play around with this animation. You could also play around with it at home if you wish. So to give you an idea of how to how does this fit in terms of how do you rotate a representative rectangle around the y-axis to obtain a solid revolution. So okay, so let's go and see how do we actually calculate the volume though. So let's look at the cylindrical shell. So I'll draw a bigger cylindrical shell here. And I'll do my best to draw this. And So basically what we see is that the distance from here to out to here, we'll call that distance R2. We'll call the distance, the interior distance, R1. Okay, and we're gonna let delta R be R2 minus R1, which is just representative of this distance right here. So this distance here is delta R. So in general, what's the volume of a right circular cylinder? It's V is equal to pi r squared h. But here we have an interior and an exterior radius, so we need to account for that. So it's pi r2 squared h minus pi r1 squared h. And we could factor out a pi h out of this expression. So we get r2 squared minus r1 squared, and that's a what? That's a difference of two perfect squares. So we can factor that even further. And we see that, in fact, delta R pops up in this factorization. Right here, R2 minus R1. What is that? That's defined as delta R. That's this distance right here. So what is R1 plus R2? Well, there's also another third distance. We call that R. R is hitting the midpoint of this thickness. So how do we find that? So R is defined as R1 plus R2 over 2, or 2R is equal to R1 plus R2. Or 2R is R2 plus R1. We could plug that in here. So we do that, and we get V is equal to pi h times 2R delta R. Or, to conclude, we get V is equal to 2 pi r h delta R. Right? That's what we get out of this. So R is the radius. It's the distance from the axis of rotation. H is the height. Okay, and we use this basically to find out what what V is. Now, in our axes, of course, we usually deal with x's, so the radius for our purposes, the distance from the y-axis, because we're only talking about rotation around the y-axis, is just going to be x. So r is going to be x, and h, the height, is usually given by some function. Usually we say that's f of x, and delta r is usually delta x. So let's see how this all comes together. So we usually say that the volume is approximately the summation of all the VI's. So that's each cylindrical shell. That's n cylindrical shells. So it's approximately this. Now, that approximation is going to be equal to 2 pi xi bar, h of xi bar, delta xi. And basically, r of xi bar, xi bar is the midpoint basically of this radius. So basically we're saying that r of xi bar, that for us when rotating around the y-axis is just x, and h of xi bar is just f of x usually, and delta xi is just delta x. So we usually write this, and then, so this is the circumference times the height times the thickness. So 2 pi r times h times delta xi, or just delta x for short. That's what we're looking at. And we add in the limit. Why? Because we are taking infinitely many shells, and we want the exact value of the volume. So V is now equal to this limit. And now we know from calculus 1 that when you take the limit of this Riemann sum, you get what's called the integral, right? So we do have an integral formula now. So v is equal to integration of 2 pi x f of x dx. And usually we have bounds on this, so a to b, 2 pi x f of x dx. When the function is rotating about the y-axis, x is usually the radius, also known as the distance from the axis of rotation. So in this instance, r sub x is equal to x. For this method, the representative rectangle is parallel to the axis of rotation. So when rotating about a vertical line, we integrate dx. When rotating about a horizontal line, we integrate dy. We'll see this later on. So the example that we first started with was y is equal to 2x squared minus x cubed, bounded by y equals 0, about the y-axis. So basically, we're looking at taking our curve, which is like this, rotating that around the y-axis, and using our volume formula. Here we're integrating 0 to 2 because we have 0 to 2 on our bounds. This is the same graph as before. 2 pi x f of x dx. And we know that f of x here is just going to be 2x squared minus x cubed in our equation. So we get 0 to 2, 2 pi x, 2x squared minus x cubed dx. And this is the setup for the volume for the solid of revolution. This solid of revolution, what would it look like? Well, it would kind of look like, here's our representative rectangle. It would kind of look like a saucer of some type if we had rotated this around the y-axis. So yes, and we can use some software to generate different 3D models or different 3D pictures, if you will, of whatever we have here. Okay, so this is just a first example of what we need to do in order to find the volume of the solid of revolution. All right, so this is just an introduction. There's going to be more examples to come. So thank you for watching.